Okay, so we are recording the session. So this is the second session for week 3, and we're going to cover t-distribution today, as well as building confidence intervals for the mean. So remember, yesterday we worked with confidence intervals for proportions. Well, today we're going to do the same thing, but for the mean. So we're going to create um, you know a confidence interval. Again, is you have a lower limit and an upper limit. And essentially what a confidence interval is a range of sort of believable values. Okay. So, and if you're outside of that range, then it's kind of like saying it's unlikely to be out of that range. And then we all know that every confidence interval has is associated with a confidence level, right? So remember we studied that yesterday. So essentially everything is going to be the same. Um, but instead of using the z distribution or the normal distribution for as we did in proportions, we're going to be actually introduced to a new distribution today called the t distribution, and and then we're going to use that for the mean. Okay, so let me share my screen, and then we can get started. Just give me a second here. All right, just one more second. Okay, so let me know if you can see my screen here. Okay. Okay, so we did problems up to problem 7 yesterday, right? So today we're going to get started with problem 8. So problem 8 involves what we call a t distribution. And just like the z distribution, it's pretty much like the z distribution. Okay, it has the same shape except it has heavier tails. You still have, area under the curve. It still looks like a bell-shaped um, distribution, and it still has, the area to the right, to the left, and in the center. You still have the level of confidence concept. Okay, everything is the same, except you'll see that for t distribution, you always have what you call degrees of freedom. Okay, so let me first just quickly draw out this. Seems like this Black Friday, I might end up buying a new tablet. This one is acting a little weird. Okay, so here is how a t-distribution looks like. So you can see it has slightly heavier tails than a normal distribution. Okay, but pretty much is a bell-shaped curve. And as I said again, you have area under the curve in the center. Okay, and in the center, remember we talked about level of confidence, right? So when we say 95% level of confidence, when I say heavier tails, I mean, so remember we used the word tail as in, what is the area on the right side, right? So this area and this area, right? And so when I say heavier tails, what I mean is this curve here, it goes further to the right and further to the left. Okay, so you have more area, on these tails. Okay, so that's what I mean. In general, it's true for t distribution. Um, yeah. Okay, so when we talked about level of confidence yesterday, remember we generally talked about 90%, 95%, 99%. So for example, if you have a 95% level of confidence, what it means is that the area in the center is 0.95. Okay, and then similarly, just like the z distribution, the area on the right and the left is going to be, so it's 5% divided by 2, so 2.5%, or 0.025 here and 0.025 here. Conrad, that's a good question. So does it ever pass 99%? Well, if the level of confidence is 100%, then what do you think? What would you think that mean if we say that the level of confidence is 100%? Yeah, you pretty much have no uncertainty, right? You're certain of your statistic, right? So that's what that means. Hi, Mel. Sorry about that. Again, I think it might have to do with your Wi-Fi connection. So if you're sort of sitting away from the hub, uh, further away from the hub, it might be due to that. So what might help is if you're closer to where your modem is, that might help. Or you can also try to log out and log back in. I hope she can hear me here. Okay, so now the only thing that's different about the t distribution, I should probably write it here, t distribution. The only thing that's different about it is what we call degrees of freedom, okay? And we're not gonna go in the details of what this is, but let me just quickly sort of first tell you the formula on how to calculate degrees of freedom. And I'm gonna represent this with df like that, okay? So small letter d and capital F. So df basically just equals, very simple, n minus 1. N is your sample size. So whatever your sample size is, just subtract 1 from it. That's your degrees of freedom, okay? So what is degrees of freedom? Well, if you have, let's just say I have a sample. So I'm just going to make up something. So say I have 2, 21. Let me just make something more realistic. 19 and 25, 22, 18 and 20. Okay, so I have 1, 2, 3, 4, 5, 6. 6 items in it. So my n is 6. So what will be my degrees of freedom? Yeah, it'll just be 6 minus 1, 5. Okay, so in this case, for this sample, my degrees of freedom are 5. But what is degrees of freedom? Well, whenever we calculate anything on the t distribution for mean, for average, notice that when I calculate the average, if I calculate the average for this data set, say I get whatever number I get, okay, so maybe I'll calculate it. So let me calculate the average for this data set. So I have 21, 19, 25, 22, 18, and 20. This is Excel. I'm going to use Excel for this. So let's now calculate the average. So there's a formula, a function in Excel, equal average, and then parentheses, and I can highlight the data set, the entire data set, and my average comes out to be 20.83. Okay, so my average for this data set, and I'm going to represent that with x bar. X bar is the sample mean, if you remember, is 20.83. Okay, so now imagine if we have this. What we have just done is we have used this data to calculate a statistic, which is the average. And you can now see that I have 1, 2, 3, 4. I can use 5 of these. 5 of these can vary. Okay. Now try to understand this. Is a little bit tricky. You don't need to know this, but I think it's good information. You don't need to know this for this homework at all. but it's just extra information. I think it'll be good to know, what is degrees of freedom. You can have, just like I calculated the average here, I can vary 5 of these values, okay? And if I have, and I can keep one of them constant, or actually, let's say if I have this 5th value is an unknown, okay? So I don't know this value, and I have the freedom to vary these 5 values, okay? If I give you the mean, if I give you, hey, this is the mean for this data set, well, you can use these 5 values to come up with, this unknown value, okay? That is what this means. So that you have degrees of freedom. There are 5 degrees of freedom, meaning you can vary these 5. And if I give you the mean, you can find the 6th value in the data set. So if your n is 6, you can vary 5 of these to find the 6th value if you're given the mean, okay? Essentially, you just work backwards. If, for example, if my mean is 20.83, the mean equals the sum of the values divided by n. If the mean is known and you know your n, the n is 6 and the mean is 20.83, you can calculate the sum, right? Whatever the sum comes out to be. And then you can take these 5. These 5 can vary whatever values they can be. But as long as you know these 5, you can take the sum, subtract the sum of these 5 values and get to the 6th value. Okay, that's what this degrees of freedom means. You have 5 degrees of freedom here. You can vary 5 to get to the 6th. All right. All you need to know for this week, actually pretty much for this course, is this formula. So make sure to remember this. Put it down somewhere so that you know how to find it. All right, so now let's do some problems. For example, here it says find the t-value such that the area in the right tail is 0.025 with 15 degrees of freedom. Okay, so the way we solve this is we go to StatCrunch. And I'm going to use stat calculator and okay, let me make this bigger. Stat calculator, and you'll see that there's a calculator for t. Okay, so this is what I'm going to use, t. And now notice, just like I said, t distribution has heavier tails. So you can see the heavier tails here. Compare it to the normal calculator. See, the tails are not that heavy. Okay, so here we have the t calculator, and the question said area in the right tail is 0.025 with 15 degrees of freedom. Okay, so df, I'll just put 15 here. My area is on the right side, and the area that is on the right side is 0.025, right? So 0.025 to the right, and if I hit compute, I will get 2.131. Okay, this part is just like the z distribution. The only difference was that it wanted you to enter df, degrees of freedom. So, and the answer here is 2.132, and you can see that it highlights the area just like the normal calculator, and it tells you that this is the critical value. I did that using calculator and t. Yes, t-stat is different from t. T-stat, we'll see what that is tonight. Can I show you the board again? I think you mean this, the whiteboard. Okay. All right, so now we just got our answer is 2.131, and that answer is correct. Okay. Find the t-value such that area in the right tail is 0.005 with 18 degrees of freedom. Okay, so it's, again, I'm going to just type 18 here, and the area on the right side is 0.005. So just like that, hit compute, I get 2.878, and you can see the area, it highlighted this tiny little area here. Find the t-value such that area left of the t-value is 0.25 with 19 degrees of freedom. So 19 degrees of freedom, area on the left side. So now I'm going to change this sign to left. What is the area? 0.25. So I'm going to put 0.25 and I get minus 0.6876. Okay. Find the critical t-value that corresponds to 96% confidence. Okay, so now you're going to help me solve this problem. And we have to assume 24 degrees of freedom. Okay. This hint is for, well, they really actually wanted you to use the tables. We can talk about it later today, but you don't really need to use these tables. All of the problems you can do using the T calculator. Okay, but maybe after the session, I can show you how to use the tables as well. It used to be that we would use tables before, the software, before, the software made this so easy to calculate. I remember using the tables in my high school, like in the 90s. I mean, really up to the 90s, late 90s, we were using these tables. And then, later on, they came up with these packages that they just calculated for you, and it's more precise. Okay, so you're gonna help me solve this. So find the critical t-value that corresponds to 96% confidence. Assume 24 degrees of freedom. How do you think I will do this problem using this calculator? Yeah, Brian. Well, luckily I remember the computers. But yeah, I mean, they were not really mainstream back then. So start with degrees of freedom. Okay. Well, first of all, let's just make sure we understand the problem. The problem says we need 96% confidence. Okay. What does that mean? So if I were to draw out the area, how would the area look like? That's my question to you. 96% confidence level. What is the highlighted area? Very good, Kimberly. It is the middle area. Okay, so this middle area is going to be 96% or 0.96. So how would we do that problem using the calculator? Conrad, that's very good. Yep, that is exactly correct. So how can we do this problem? Use between. Very good, Sal. I'm going to use between. And so the area in the center is 96. So I'm going to type 0.96. And what about the degrees of freedom? Degrees of freedom that's given in the problem was 24. See, it says assume 24 degrees of freedom. So I'm going to use 24. Okay, and then I hit compute, and here's the answer. The lower limit is minus 2.17, upper limit is 2.17. So this is the answer, 2.172. That's the critical value. That makes sense? So as you can see, not that hard, right? Just like the Z distribution. Now let's do some problems here. Okay, this problem is actually pretty easy. So determine the point estimate of the population mean. So we're not talking about proportions anymore. And the margin of error for this confidence interval. Okay, so here's the lower limit is 20, upper limit is 30. So let's draw it out. So remember we said here's the lower limit. Now it's given as 20 and this is given as 30. So where is the point estimate? Where is the point estimate here? Very good, in the middle. Now, in this case, actually, let me just highlight it using something different. Here's the point estimate. Okay, what is the point estimate in this problem? What is the point estimate? I'm not asking for the value. I'm asking what kind of point estimate are we interested in? It is the mean. Very good. It's not the proportion anymore. It is the mean. So this is the mean now. So, and a lot of you already know what this should be. It should be 25. How did we calculate it? Well, it's in the middle, and we know 25 is in the middle of 20 and 30. If you wanted to calculate it, you can just do 20 plus 30 divided by 2. This gives you the center. So it's 25. Okay, so that's your 25. Now, what is the margin of error in this case? What is the margin of error? Excellent. It's 5. It's the difference between the upper limit and the mean or the lower limit and the mean. Okay, should be the same. It is 5 in both cases. It should be the same. So it's 5. Excellent. That's what the question was. So this is actually very much like the proportions, right? Except we're not going to be using the mean. So, right? Very good. Okay, now in this problem, in a survey, 1,400 adults in a certain country were asked how many hours they worked in the previous week. And based on the results, a 95% confidence interval for mean number of hours worked was, here's the lower bound and here's the upper bound. So obviously the lower bound they think is 40.7, the upper bound is 44.6. So which of the following represents a reasonable interpretation of the results? So basically we just have to understand how do we interpret this confidence interval? What is the correct interpretation for this confidence interval? So here's the first part. There's a 95% chance the mean number of hours worked by adults in this country in the previous week was between 40.7 and 44.6. Not right. What is the problem with it? The problem is that we're associating 95% chance with the mean number. Now, what that inherently means is that we think that because there's a chance associated with the mean, what that means is that we're saying that the mean, the average, will be varying or will move, okay? Because we're associating chance with it. The easiest way to remember what is the correct interpretation is, first of all, this should be confident. You should be using the word confident or confidence with 95%. Okay, the chance, whenever you use the word chance, it means you're associating probability with, a statistic, meaning that the statistic can move. That's wrong. This is wrong. We are 95% confident that the mean number of hours worked by adults in the country in the previous week is between 40.7 and 44.6. This is correct. Everything in this statement is correct. It tells you that how confident you were, 95%, and it tells you that the confidence level, the confidence interval, the lower limit is 40.7 hours and the upper limit is 44.6 hours. Okay, so this is correct. 95% of adults in this country worked between this and this hours last week. Wrong. Here you're associating proportion. You're using 95% as almost like a proportion of adults. So meaning now you're implying that that this 95%, which is actually the confidence interval or the confidence level, you're associating that with the number of individuals. Okay, you're not saying you're not associating your confidence with respect to the confidence interval. So this is what's wrong about it. You cannot use 95% as a proportion in this confidence interval. So that's wrong. We are 95% confident, so far is correct, that the mean number of hours worked by adults in a particular area of this country in the previous week was 40.7 and 44.6. This is wrong because look at the problem statement. By the way, B and D are very much the same. B was correct. D is almost like B, but there's one problem with it. The problem is here. You're saying in a particular area of the country. Nowhere in this original problem did it say that this is a particular area of the country. It said 1,400 adults in a certain country were asked how many hours they worked, and this was the confidence interval. You cannot take that confidence interval and apply it to a smaller region of that country. Okay, the confidence interval is built using data from the entire country. So you cannot just take that and say that all these small regions will have the same confidence interval. That's incorrect. So that's what's wrong about it. So you can see it says flawed. The interpretation should be about the mean number of hours worked by adults in the whole country, not about adults in a particular area. Okay. Does this make sense? I think it's fairly straightforward. I hope I was able to explain it clearly. Interpretation is an important piece of of confidence intervals. Awesome. How many students are here tonight? 31. See, the crowd is getting smaller and smaller. Okay. All right. Now let's look at problem 11. A nutritionist wants to determine how much time nationally people spend eating and drinking. Suppose a random sample of 945 people age 15 or older. The mean amount of time spent is 1.16. Standard deviation is 0.73. I'll show you why they actually gave you standard deviation. Okay. But let's read the problem. A histogram of time spent eating and drinking. So when they created a histogram of the data, they found that the histogram is skewed right. So meaning you have outliers in the right direction. So large numbers, you have some large numbers. Use this result to explain why a large sample is needed to construct a confidence interval for the mean. Now, the reason you need a large sample is because if you have a skewed distribution, then your mean will be skewed, right? Your mean will be skewed in that direction. Remember, we did this during week 1. So in order for your sample mean, the distribution of the sample mean to be approximately normal, you will need a large sample size. That's what you need. We did this last week when we talked about the central limit theorem. I don't know if you remember that, but in central limit theorem, we talked about when we have a distribution of means, which is, remember, the mean of the means, the mean of many, many, many means. When you keep taking samples, and I showed you no matter what the distribution is, original distribution is, even if it's skewed or whatever, the distribution of sample means will always be normal as long as you have a large sample size. Okay, the larger the sample size, the more normal the distribution will be. So this is the correct answer. It's just the reason why you need a large sample. Because if you cannot use this bell-shaped distribution for the sample mean, you can't do these calculations that we're doing because you know you want your distribution to be approximately bell-shaped so that we can do these calculations using the normal calculator or the T calculator. Okay, now in 2010 there were over 200 million people age 15 or older. Explain why this, along with the fact that data were obtained using a random sample, satisfies the requirement. There's only one requirement, okay? And the requirement is that your sample size should be less than 5% of the population. So the means is your N should be less than, and it can be equal to 5% of the big N, the population size. In this case, the population size is 200 million. And we have to calculate 5% of that. So what is 5% of 200 million? It should be 10 million, right? 10 million. So 5% of 200 million is 10 million. And let me show you how I got that. So just forget the M for million for now. Just say it's 200. 5% of 200 is 10. So now you have 10 million. Okay. So 10 million. So 10 million should be your limit. So is your N less than or equal to 10 million? Yes, it is, because your small n is 945. That's the sample size. So 945 is much less than 10 million. So the conditions are met. Okay. Okay, now we have to determine and interpret a 99% confidence interval for the mean amount. So we have to build a 99% confidence interval. Okay. So how do you know the correct sample size? Well, in this problem, sample size is given to us. It's 945, right? So that's the sample size we have to use. The limit of the sample size that we can use is 10 million. So obviously, the larger the sample, the better. If we can do 10 million, then that's great. But in reality, we can't, right? Usually, the case for the sample size is that do as much as possible. And if you cannot do that many, then you have to do some precision calculations. In fact, one of the problems tonight is going to be on that. So we'll get to that. Okay, so what we need is, these are very good questions, Alfred. Very good question. All right, so what we need is to find a confidence interval for the mean. So I'm just going to say CI, confidence interval for the mean. Okay, and here's the formula for it. First I'm going to do it with the formula, and then I'll show you how to do this in StatCrunch. The formula is X bar plus or minus. Again, this will give you a lower limit and an upper limit. The T alpha over 2, which is your critical T value, times S over square root of n. This S is the standard deviation, okay, which is the reason why this problem gives you standard deviation. And n again is the sample size. Is that easy? So for example, in this problem, you're given X bar as 1.16. You're given S as 0.73, and your N is 945. Okay. And I can find my T, my critical T I can find. So let me find that. And recall that we need 99% confidence interval. Okay. So let me find my T, critical T value first. So I can go to StatCrunch. And how do I find that? I'm just going to type 99 here. But what do I type for DF? What is my DF in this case? Can you tell me what my DF should be in this problem? It should be n minus 1, and Jerica and Sandra is correct. It's going to be (944). Okay, because it's just 945 minus 1, 944. So that's my degrees of freedom. Need 99%. And here are the T values I'm going to use. 2.581. So the critical T is 2.581. Okay, so now I can find my confidence interval. It's just the lower value of the confidence interval is X bar minus T S over square root of n. So X bar is 1.16 minus 2.581 times 0.73 divided by square root of 945. Let me just save some space here. This is my lower limit. What is the upper limit? Or the upper value is 1.16 plus all of this. Okay? Okay, I'll stop. Okay. Now, do you all agree? I will let you do the calculation, but do you all agree I can find this and I can find this? Do you all agree with that? I mean, I have everything I need. This is just arithmetic now. So I'm sure you can do these calculations, right? So here's the StatCrunch part. I wanted 99%. I typed 99 here, 0.99, degrees of freedom 944, hit compute, and I get 2.581. So you all agree with me that I can find these values. This is just arithmetic now. Okay, so this is how StatCrunch will do this. It uses this formula to give you the confidence interval just like this. Let me show you how that works. Now, you're going to use stat, and instead of using proportion stats that we did yesterday for proportions, we're going to use t-stats for confidence interval for the mean. Okay, so I'm going to use t-stat, one sample with summary. And the rest is very simple. It's just you plug in the values that are given to you. The mean is 1.16, standard deviation is 0.73, sample size is 945. Switch this to confidence interval and type 0.99 because you have a 99% confidence interval. So 0.99 and hit compute, and you get your lower limit and the upper limit, and it is 1.098 and 1.221. How easy is that, right? But now you know how StatCrunch actually does this. It actually does these calculations in the background. Okay, so what did I do? I went to t-stats, one sample with summary, typed out all these values. Notice I didn't have to type the degrees of freedom because StatCrunch calculates it itself. And I chose confidence interval for mu, for mean, and I put 0.99, and I got my answer. And that is the answer to this problem. Oops. So the answer is the nutritionist is 99% confident that the mean amount of time spent eating or drinking is between 1.099 and 1.221. Okay. Now here's a problem. Could this interval be used to estimate mean amount of time 9-year-olds spend eating and drinking? What do you think? This was for people age 15 or older. So could we use this to estimate mean amount for 9-year-olds? No, can't do that. No, because the interval is about people aged 15 or older. Mean amount of time spent eating or drinking per day for 9-year-olds may be different, right? So it might be different, so we cannot use this interval for 9-year-olds. Okay. So this is it. I mean, pretty much this is it. This is how we're going to do the rest of the problems. So here's another problem. Based on interviews with 98 SARS patients, researchers found that the mean incubation period was 5.4 days. Here's the standard deviation. So you have your mean, the standard deviation, and the sample size. And here's your level of confidence. Okay, so you're going to calculate the lower and the upper bound. So how about you help me solve this problem? Okay, so here's the problem. How can I do this? So again, we're trying to find the confidence interval for the mean. Stat, t-stats, one sample with summary. Very good. That's okay. So I have my summary. What is the mean given in the problem? 5.4. I'm going to type 5.4. What is the standard deviation? 14.2. What is the sample size? All right, 98. Very good. And what else am I going to do? Choose confidence, and it's already 0.95, so I'm going to leave that as is, and very good. That is it. I'm just going to hit compute, and we get the lower limit and the upper limit. 2.55 and 8.25. Excellent. Okay, so you have to round it to 2 decimal places. So very good. And then we have to do the interpretation, and the interpretation is that there is 95% confidence that the mean incubation period lies between the lower and the upper bound of the interval. Notice all B and C are incorrect, even though they say confidence, but the first one says that the mean incubation period is less than the lower bound. The second one says it's greater than the upper bound. Well, that's wrong. The correct interpretation is that it's between the lower and the upper bounds, right? So D is correct. A is wrong because, again, it's using the word probability with 95%. That's not right. Okay, any questions so far? I think it's fairly straightforward. Great. Okay, so now we have a little bit of an interesting problem. I think this is a good problem to do. So here, now you have been given the data, okay? You're not given the summary. You're actually given the actual data. It represents the asking price for a simple random sample of homes. So these are asking price for homes. And how many are there? 4 times 3, 12. 12 of those. Construct a 99% confidence interval with and without the outlier included. Okay, first of all, looking at this data, let me first open this in StatCrunch. Okay, so I'm going to use this box, click on open in StatCrunch. Okay, so here's the data. What I would like you to do is go through this data real quick, just take a look at this and tell me where is the outlier. Tell me the value of the outlier. Very good. The outlier is right here, okay? It's 460,000. All the other values are fairly, within each other, right? Within the range of each other. 143, 180, 147, 219, 264. All of these are close enough, except this one, which is like way out there. That's the outlier. So what they want you to do is they want you to calculate a confidence interval for the mean when this outlier is included and when this outlier is not included. Okay, that's what they want you to do. So what I'm going to do is I'm going to just label this, say, W outlier, meaning it's with outlier, and I'm going to label this as WO outlier, without outlier. And I'm going to copy this data. So I'm going to highlight it, just copy using Control C, and then take the cursor here and just paste it, Control V, and then I'm going to just go here and delete this value. Okay, so now here's the data, same data set without the outlier included, and here's the data set with the outlier included. Okay, and all we have to do is calculate the confidence interval for, with the outlier included and without the outlier. So what do? We're going to go to Stat. We're calculating confidence interval for the mean, so I'm going to go to T-stats. I'm going to use one sample, and instead of with summary, I'm going to use with data. Okay. Okay. Now I can do both at the same time. So I'm just going to highlight both of these. Okay, now this looks different because remember, we don't know the mean and the standard deviation, right? We can calculate them using the sample, but we'll just let StatCrunch do it for us because we selected the option with data, not with summary data. So because we selected the option with data, it's going to calculate the mean and the standard deviation in the background. Okay. So that's why all we have to do is highlight the columns. Where is the data located? Okay. So this is with outlier, without outlier. I got that. And now we are going to choose confidence interval and we need 99% confidence interval. So I'm going to change this to 0.99. Okay. And here's the answer. See how nice it is, how quickly it calculates it, and you don't have to do any calculations using the calculator or anything. Okay, so with the outlier, this is your confidence interval. Without the outlier, this is the confidence interval. So what's happening? What happens when you don't have the outlier included? Do you see any difference between the two confidence intervals? And if yes, what is the difference? Very good, Brian. You can see that the confidence interval without the outlier is narrower, right? Can you see that? It's narrower. So if I were to draw it, let me draw it out. It looks something like that. With outlier, I have the lower limit is 151, 119. The upper limit is 302, 047. Okay, this is what I'm getting. Now without the outlier, I'm going to try to draw it at the same scale. My interval is from here to about here. The lower limit is 164 and the upper limit is 246. Okay, so I want to apologize for not drawing straight lines here, but this is what it is. And this should be somewhere, it probably should be shifted a little bit this way. But anyway, I'm going to exaggerate it a little bit. So, okay. So you can see that without the outlier, the interval is narrower. Do you all agree with that? Do you all agree that it's narrower without the outlier? Okay, so now what do you think why that is? Why is that true? Let me put down the formula for what we just calculated. This is the formula for the confidence interval. Why is it that it's narrower without the outlier? Well, not really with it being exact. There's something in this formula that's causing this to be narrower. Very, very good, Sandra. Excellent. With the outlier included, Sandra says, when you include the outlier, there's more variation in the data, right? When there's more variation in the data, your standard deviation is going to come up to be higher. So it's higher for the outlier included than the outlier not included. Because the standard deviation is higher, you can see that this whole value, if I just use, let me just use, this is the margin of error. We all agree with that, right? This is the margin of error. This is ME. When the outlier is included, you get a larger margin of error. Do you all agree with that? When the outlier is included, margin of error is higher because of this standard deviation, right? When you have a higher margin of error, you will be subtracting more and adding more, right? You will be subtracting a higher value and adding a higher value, which is why you will get a wider confidence interval when the outlier is included. When the outlier is removed, you get a lower value of standard deviation. So now your margin of error is lower. But now you subtract a lower value from the mean and add a lower value to the mean to come up with your confidence interval, which is why your confidence interval is narrower now. Okay, so does this make sense? Does this make sense? Does this now, can you connect why this is happening? It's happening because, just like Sandra said, it's happening because this outlier introduces more variation in your data. So your standard deviation goes up, meaning now your margin of error goes up and you get a wider confidence interval. Okay, that's the reason why this is happening. Okay, so comment on the effect on the outlier. Well, the outlier caused the width of the confidence interval to increase. When the outlier is included, you get a wider confidence interval. Okay, that's it. And then let's go to the last problem. So a doctor wants to estimate the mean HDL cholesterol of all 20 to 29-year-old females. How many subjects are needed to estimate the mean HDL within 3 points, 99% confidence when your standard deviation is this? Okay, so let me just write down all this data. So what we need is in the first part of the problem, we need 99% confidence. That's how confident we need to be. Standard deviation that we're targeting is 10.7. And we want the margin of error to be, it says within 3 points. So margin of error is plus or minus 3. So again, the total width will be 6. Okay, just like yesterday, we did a problem like this. StackCrunch will take the width and not the margin of error. Okay, and the question is, what should be my sample size? Okay, if I want the margin of error to be 3 plus or minus 3, this is my standard deviation, this is the width, and this is the confidence interval. So remember, we said this is how we calculate the confidence interval for the mean. This part is the margin of error. Now, I can rewrite this. Let me just rewrite this here. ME equals T times S over square root of N. Okay. All I have to do is just solve for N here. That's all I have to do. And when I do that, I will get this. Now, do you all agree with me that S is given? Here's S. The margin of error is given. Here's the margin of error. And I can find my T because I've been given the confidence level, 99%. Do you all agree I can find all this? And I can square it then, and I'll just find my N. It's very easy. It's just arithmetic, right? Everything is given to us. So, but the nice thing is that StackCrunch will also do this for us. And it basically just calculates this, uses this formula to calculate N. Let me show you how that works. So in this problem, here's the problem data. So what I'm going to do is I'm going to go to stat, tstat, one sample, and I'm going to use width and the sample size. Okay, remember we did this for proportion yesterday. All right, so now I want my confidence level to be 0.99, 99%. Standard deviation given is 10.7. The width is 6. Remember I said the width is 6 because the margin of error is plus or minus 3. The total width therefore is 6. And I can find my sample size. If I hit compute, it finds my sample size. It says the sample size should be 89. That is the correct answer for this problem. So someone had asked before, what is an appropriate sample size to use? And I said the larger the better. But when you are given this precision, what you are trying to do in real life is you're trying to find the minimum sample size so that you don't have to put more resources on that extra sample, right? So you want to find the minimum required to meet your precision that you're targeting. In this case, the precision is you want your margin of error to be 3 points, plus or minus 3. You want to be 99% confident in your estimation, and you want your standard deviation to be 10.7. Okay? Based on this, what's given, you will need 89 sample size. Now, if you are able to do 100, that's awesome. You will reduce your margin of error by taking more. Okay? So that's great. But um, but can I explain the width? Okay, the width is just 6, right? Because margin of error is plus 3 and minus 3. So this is my confidence interval. This is the mean, right? This is my margin of error, plus 3. And here's the margin of error, minus 3, right? The total width is 6, right? Well, what it does is, let me just do this again. What it does is it tries to, the algorithm it's using to find the sample size, you know, it's an algorithm that is trying to converge to a value. And I don't want to go too much in the detail of how it's doing that, but when it does that, it changes the width to come to a whole number. Okay, and that's why. So it will never give you 89.6, for example. Okay, the sample size you may get when you do that calculation, you might get something in decimal points. But what it does is instead of giving you decimal points, it gives you whole numbers and it changes the width, okay, a little bit to get to that whole number. That's what it's doing. Okay, and Kimberly, so Kimberly, if the margin of error was plus or minus 2, then your width will be 4. Okay, if you can just sort of understand this diagram here, plus or minus 3, then you know that the total width is 3 plus 3. 3 in this direction, 3 in this direction will give you total 6. Oh, it will change that answer, Rob. If my width, if I want a lower margin of error, what do you think will happen? Do you think I will need a larger sample if I reduce my margin of error? Yeah, I'm going to need a larger sample. So if I reduce this to 4, say I want my width to be 4 now instead of 6. Take a look at this. I need 194 sample because I want, when I reduce my margin of error, then what's happening is I'm saying I want my estimate to be more precise because my margin of error now is lower. If I can live with a larger margin of error, say I want 10 now instead of 4, you'll see that I'll need fewer cases, 35, because I'm saying, I can live with a larger margin of error, meaning I'm okay if I make errors, you know, so I have more room for errors, and I'm okay with that. So that means I can live with a lower sample size. Okay. So we had 6, and so we need 89. Okay. Just like this, if I keep this the same and I reduce my confidence level, now I want to be less confident. Well, then my sample size will decrease because I'm okay with living with less confidence. I don't need to be very, very confident. Okay, so I'll need fewer cases. Now, this is the second problem, by the way. Second problem says, what if we have all this, but now we need 90% confidence? Okay, so everything else remains the same. This will be 6. Standard deviation is the same. But I now go from, so just let me just do the first one. So remember we did 99% and we got 89, right? Sample size. Now I'm going to do 90% because I'm okay with being less confident. Well, if I hit compute, you'll see I get a lower sample. I'll be okay with a lower sample size. So 37 is the answer for this. So what's happening? What happens when I reduce my confidence level? Well, decreasing the confidence level is decreasing the sample size. Increasing the confidence level will require you to have a larger sample. Okay? And just like that, the margin of error works the same way. When I was using margin of error of 3 so that the width was 6, I got 89. But when my width increases, I'm okay with the larger error, my sample size decreases. But if I want to be very, very, very precise, if I want my width to be, say, 2, this is a very precise estimate now. My margin of error is only 1. Then my sample size is really large. I need 764 cases. Like that. Yep. Isn't that nice? Yeah, so what it's doing is it's using an algorithm that tries to converge to an answer. And you can see it never gives you, a decimal point answer for sample size because that will not make sense. You can have decimal points in your answer, right, for sample size. So it always, when you enter something, first what it does is it gives you a whole number, closest whole number, and then it just changes the width a little bit to get to that whole number. Okay. So does this make sense? These are your answers. Decreasing confidence level decreases the sample size. That's exactly right. You can't poll 89.6 people, right? That's right. Okay, and that's it. So actually we're done early tonight. We have an early finish to the session. Actually, I feel like the confidence interval for mean is easier to calculate than proportion, isn't it? Increasing the margin of error decreases the sample size. Yes, Sandra, that's right. So the theory behind that is when you increase the margin of error, what you're saying is, hey, I can live with making more, sorry, let me rephrase that. I can live by having a larger room for error. And because I can live with having a larger room for error, I need fewer cases. If my margin of error is lower, what I'm saying is I cannot live with a larger room for error. Okay, I only have a very, very small room for making an error. And because now I have a very small room for error, I need a larger sample size so that there's less chance for me to make an error. Does that make sense? Okay, question 8, part D. Okay, question 8, part D said, "96% confidence level." So I have my T distribution. 96% is in the center, right? This is 96%. I need to find these values. These are the critical values I need to find. And I have 24 degrees of freedom. Okay. So for that, I can just use calculator and T. Okay, I can use the T calculator, 24. I'm going to use between, by the way, first of all. I'm going to use between option, 24 and 0.96. and I get 2.17. Okay. Okay. Let me just run through the questions first. On 6, do I need to just convert decimal? Okay, problem 6. So this is the same problem, Mel. So what you can do is go to StatCrunch, and this time, because we're using proportions now, I'm going to go to Stat, Proportion Stat, One Sample, and Width and Sample Size. So once I'm there, for the first part, I'm going to say, so notice I need 90% confidence, so I'm going to use 0.90. My target proportion, it tells you, is in the first part is 0.52. The width here, margin of error, is 0.02. See, it says within 0.02. So my width is going to be 0.04, twice the margin of error. So it's 0.04 here. And I hit compute and I get 1689. That's the first answer. For the second, we have a target proportion of 50%, 0.04, because remember I said 50% is when it's the worst case scenario. So you're going to use 50% for part B, 0.04. And what just happened? Target proportion is 50, confidence interval. Really? Okay, that's odd. 90%. It really did this. Okay. That's really odd. Now it's doing it right. I don't know what happened previously, but anyway. Yep, so you just use 50% for part B. Okay, there are a lot of questions on this, and I think this is something you'll have to visualize to understand. So please try to visualize it. Otherwise, this will be very confusing for you. As I said, when you have a confidence interval and you have the mean in the middle, or the proportion in whatever you have in the middle, the point estimate, right? So I'm just going to use the mean. This is your margin of error. The problems will give you margin of error. So when your margin of error, say, is 2, if your margin of error is 2, then your width is the whole thing. It's the width is the width of the confidence interval. If your margin of error is 2, then your width is 2 times 2, right? 2 in this direction and 2 in this direction, right? 2 in this direction, 2 in this direction. So 4. Now say that your margin of error is 3. What that means is it's 3 in this direction, 3 in this direction. So total width is 6. 3 plus 3, 6, right? So all you have to do, just like Vince said, is double the margin of error. Whatever margin of error is given to you, just multiply it by 2, and that's your width. And the reason why we do that is because the calculator wants the width. It does not want the confidence interval, the margin of error. It wants the width. So that's why you multiply it by 2. Okay, now can you explain how to get to n when trying to figure out the sample? Well, it's going to be the exact way I showed. For example, when you have the mean, my confidence interval is based on this, right? And my margin of error in this equation is t times s over square root of n, right? So yeah, sure, that's okay. So this is the way to get to it. So when we have the mean, right? When we have the mean, this is the equation, right? This whole thing is the margin of error. So I'm just going to rewrite it here. ME equals TS over square root of n. And all you have to do is solve for n in this equation. When you solve for n, you're going to get TS over ME, and you're going to square it. Does that make sense? You just bring this here, and square it. So now this is your standard deviation. This is your margin of error. And this is the T. This is the critical T value. So if you have 99% level of confidence, you'll have to find your T value. That's how you get to N. By the way, nobody asked me this question, but someone should have asked this question to me. Do you notice we have the T distribution here, right? Do you notice, I mean, I think you should have noticed that T involves calculating degrees of freedom, right? Using n minus 1, right? df is n minus 1. But no one asked me, in this case, we don't know n, right? We're actually trying to calculate n. So how do we know what n minus 1 is for this t, right? Does this problem make sense to you? Okay. So for critical t value, right? The critical t, remember we solved some problems where we said, okay, if I gave you 99% confidence, you said the middle area is 0.99, and this is a t distribution. Remember when we used the t calculator, it wanted you to enter degrees of freedom, right? Do you all agree with that? When we use the t calculator, it wanted a value for degrees of freedom df, right? Before it gave you this answer. Okay, good. Now, the problem here is I'm using t here, but I don't know my n. I'm actually trying to calculate my n, right? I'm trying to calculate what n should be, but I cannot have t here because t actually wants n already to be calculated, right? I can't use t here because I have to know my n to come up with the t, right? Because of this problem where I need to know my degrees of freedom. And I don't know those because I don't know my n. This is unknown. I'm trying to calculate it here using this equation. So what's the solution for this is very simple. All you do is instead of t, you just use z. So when you're trying to find your n, just use z because z does not involve degrees of freedom. You don't need to know degrees of freedom for z. That's all you need to do to get to n. Okay? But essentially, this is what you have to do. I don't know who asked this question. Was it Peter or Vince? Vince asked this question. Yes, Vince. So this is what you have to do. Okay? Absolutely, yes. You get z from the z table, or you can use the normal calculator in StatCrunch. Okay? So that's how you're going to do it. But luckily you have StatCrunch and it does it for you. You don't need to do any of this manual steps. So, and by the way, Vince, just so to add to your understanding here, the whole concept of calculating n relies on what is the standard deviation of the distribution that you're targeting. Okay, you have to know something about the standard deviation. And then you also need to decide what should be your margin of error. What margin of error are you happy to live with? Okay. If your margin of error is lower, then you're going to need a larger sample. If the margin of error is higher, you need a smaller sample. Okay. Yes. Yes. Okay. And then similarly, the proportion is the same way. Yes, that's right. Let me just show you that. So that is going to be stat, t-stats, one sample, width, and sample size. Okay. So does that make sense, Vince? Does that help you understand the sample size, why we, or how we calculate it and why? Okay, great. Okay, so any other questions on this? So by the way, a lot of people, I see that several of the students have left, but I was hoping maybe I can talk a little bit about the calendar that week, that 1 week of Thanksgiving. So Thursday is Thanksgiving. So do you think maybe how about we do Tuesday and say Wednesday? Would Wednesday work better or Friday for the second session? Everyone says Wednesday because they're going to be traveling Friday probably. Okay, looks like Wednesday is has more votes, so we're going to go with Wednesday. Well, what if we had the choice of Monday and Wednesday? Monday might be tough for me, but I can check it. I can let you know next week. Either is fine Wednesday. Okay, so maybe we'll just do Wednesday if that's okay with everyone. Sounds good. We'll do Tuesday and Wednesday for that week. And the next week we'll go back to the regular Tuesday and Thursday. Okay. Any other questions? Questions, complaints? Yes, everything will be, yep, all sessions are recorded, so I'm going to record that as well. Okay, any questions? As I said, questions, complaints, feedback. Will there be a reminder for those? Yes, I will update the calendar tonight. Alfred, I would say a good resource, just go to Google and type sample size calculation and see what you come up with. There are tons and tons of um, links there. So any one of them will do. Will we have to remember all of this for final exam? Yes, Vince, you're gonna have to know how to do all of this stuff. Everything that we're covering in the homework assignment will be part of the final exam. But the nice thing is you will be able to use StatCrunch. So the more you practice, the better. And there will be a final exam webinar review. I'm sure you'll feel much better, once we go through that. That will be in week 8. Vince, I assure you, once we go through the webinar session for the final exam, you'll feel much, much better. Because essentially what I have done for that session is I've come up with a set of problems that are very much the same like the final exam, and I will go through those problems. I'll show you how to do them in StatCrunch. It will be like a reminder of everything you've done so far, so you'll feel much better. Oh, thanks, Sandra, for answering that question. Yes, Kathy. So Kathy, the calendar that Sandra mentioned is posted in your Blackboard. If you go to the Blackboard shell for the course, click on webinar information, and then if you scroll down, you'll see that calendar. And it's also on Professor David's website. All the webinar recordings I also post them on Professor David's website. It's right here. So if you just click on that link, you'll see the webinar links. And I will post the one tonight as well. Okay, I'm going to stop the recording and then